Let's begin our study of polytropic processes by first looking at the equations that describe a polytropic process. And then we want to do some integral calculus and see if we can't simplify the work performed by a polytropic process from calculus to an algebraic expression. So what is a polytropic process? Well, it's a process that follows this equation, where PV to the n power is equal to a constant, where P is the pressure, V is the volume, and N is just any number between 0 and infinity. And we could also say that the pressure times the specific volume to the n power is constant. Specific volume is just volume divided by mass, and since mass is constant, we can use either volume or specific volume in the polytropic process equation. Now, when n is 0, it's easy to determine that we're dealing with a constant pressure process. If n equals 1, it turns out that it's a constant temperature process. And if n is equal to k, we have an adiabatic process. An adiabatic process being one that has no heat transfer. Now, what is k? We haven't gotten to this yet in our studies. But K is simply the ratio of specific heats for a gas. It's the ratio of C sub P over C sub V. And for room temperature air, K is about 1.4. So if we had room temperature air involved in a process, and N is 1.4 and K was 1.4, then that would be an adiabatic process. And finally, when N is equal to infinity, we have a constant volume process. So let's calculate the work done by a polytropic process. We can write that work is the integral from V1 to V2, that's the volume at state 1, to the volume at state 2 of P to V. And remember, P times V to the n power is a constant. That's the basic equation for any polytropic process. So if we know P and V, we can solve for the constant C. So we can write C in a couple of ways. We can say it's P1 V1 to the n power, or P2 V2 to the n power. And since we're going to integrate pressure with respect to volume, we need to write pressure as a function of volume. So rearranging this equation, we can say that the pressure is this constant C divided by V to the n power. So let's substitute C over V to the n power for pressure in our integral. And now we have that work is the integral from V1 to V2 of C over V to the n power dV. Well, C is a constant. We can remove that from the integral sign. And we end up with work is equal to our constants times the integral from V1 to V2 of 1 over V to the n power dV. So now we can integrate this integral, and we'll have to do it two different ways. One with n not equal to 1, and then we'll do it again with n equal to 1, because they'll integrate differently. Well, in the first case, where n is not equal to 1, the integral gives us this algebraic equation. The work is equal to C times V2 to the 1 minus n power, minus C times V1 to the 1 minus n power, all over 1 minus n. Well, let's substitute a value for C. Now, in this first term, because I'm multiplying times V2, for convenience, I'm going to choose C as P2 V2 to the n power. And in the second term, where I'm multiplying times V1, I'm going to choose, for convenience again, C is equal to P1 times V1 to the n power. Well, this simplifies quite easily, and I get that work is equal P2 V2 minus P1 V1 all over 1 minus n, and that's when n is not equal to 1. Now, when n is equal to 1, I'm simply integrating 1 over V to V, and we know that is the natural log of V. And since we're integrating from V1 to V2, we're going to end up with the natural log of V2 over V1, but we have to multiply by our constant C, which we'll take as P1 V1. So in the case where n is equal to 1, the work is equal to P1 V1 times the natural log of V2 over V1. So now we have this expression for work of a polytropic process when n equals 1. And we have this expression for a polytropic process work term when n is not equal to 1. Well, what happens when n is equal to 0? Well, in that case, we would use this expression here where n is not equal to 1, because 0 is not equal to 1. Well, if we plug in of 0 in here, we end up with a denominator of 1, so it disappears. And we just end up with P2V2 minus P1V1. But P2 is equal to P1 in a constant pressure process. And so in a constant pressure process, we can reduce this term to the work is just the pressure times the change in volume, which is V2 minus V1.